Hi, in this video, we will discuss about the sound level meter. We know that the sound level meter is an instrument that is designed to respond to the sound in approximately the same way as the human ear. Sound level meter provides an objective and reproducible measurement of sound pressure level. The functional schematic diagram of the sound level meter from the microphone to the display are provided here. Microphone is the most expensive component in the sound level meter. It's used to convert the sound pressure signal into electrical signal. So the engineering unit in this case is the sound pressure, and it will be converted to the voltage by using the transducer, which is the microphone. The conversion between the sound pressure and the voltage can be done by using the sensitivity curve here, as shown in the red curve. The measurement range of the microphone must be in the linear range, where the sound pressure is linearly proportional to the voltage. Outside this range, you can see that the red curve is no longer linear. Therefore, the measurement of pressure in this range is invalid. From the figure, you can see that the valid measurement range is only from 0 dB to 150 dB. In terms of formula, we know that for a valid measurement, the voltage must be proportional to the pressure. So we can obtain V equal to SP in this case, where the S is the sensitivity. By rearrange this formula, you obtain sensitivity is equal to voltage per unit of pressure. When we buy a microphone, the sensitivity of the microphone will be provided by the manufacturer. So once this is provided, we can use this formula in order to convert the pressure into the voltage signal. Microphone can be made based on the piezoelectric principle, inductive principle, condenser principle, as well as the electric principle. The most stable type of microphone for the sound level meter is the condenser microphone. This is because it has good precision with good stability and reliability. This is the schematic diagram for the condenser microphone in 3D and 2D. At the outer surface here, we have a diaphragm, which is electrical conductive. When the sound wave hits to the diaphragm here, the diaphragm will moving back and forward relative to the backplate, which is located here. So in this case, the distance between the diaphragm and also the backplate will be changed. As a result, the capacitance will change according to the rhythm of the sound wave. In this way, the sound pressure can be converted to the electrical quantity in terms of capacitance. The size of the microphone here will affect the useful frequency range for the sound measurement. For an ideal microphone, we will have pressure versus frequency in such a manner, where you can see the frequency response here is flat. The sound measurement is valid within this range, which is around 1 to 200 kHz here. Then we can identify the useful frequency range for the microphone here. Ideally, it is desired to have a microphone that has wide and flat frequency response like this case, where you can see the useful frequency range is around 200 kHz. This frequency range is more than sufficient for the acoustic application, where we only need 20 to 20 kHz. Remember, this is for ideal case, where it's desired to have a larger and broader frequency range as possible, but in actual is limited by the size of the microphone, where you can see when the size is smaller, the frequency range is larger, but when the size of the microphone is larger, then the frequency range will be reduced. If you want to measure the sound pressure at 120 kHz, which size of the microphone you should choose. So if you choose the first one, we cannot measure this because it's out of the range. So if you look properly, only the last microphone here is suitable because it can cover the range 6 to 140 kHz. Therefore, we can measure this sound wave. What if you want to measure the sound wave around 1 kHz? Which size of the microphone you should choose? So in this case, you see that all the microphones satisfy the frequency range. However, the larger size of the microphone has larger magnitude of the voltage. However, for lower size of the microphone has lower magnitude of the measured voltage. If higher amplitude sensitivity is desired, then we can choose a larger size of the microphone. Previously, we have learned that by reducing the size of the microphone, the useful frequency range will be increased. From these figures, it shows that smaller microphone has a smaller range of the useful dynamic range. If you choose the microphone with 1/8 inch size for the sound measurement, then the measurement range is only applicable from 70 dB to around 170 dB. The useful dynamic range increases when we choose a larger microphone. For example, in this case, we choose the 1 inch microphone for the sound measurement. So you can measure the sound with the range from 0 dB up to 150 dB. So we need to trade off between the useful frequency range and also the useful amplitude range when we select a useful microphone for a particular case. After the microphone, the electrical signal will pass to the preamplifier. The electrical signals produced by the microphone are very small, which is located here, and we need the amplifier, which is given by this symbol. So in this case, the amplifier can increase the signal several thousand. Let's assume it can be increased by 1000 times the original signal. Therefore, after the amplifier, you will obtain 10,000 milliwatt of the signal. Compared to the noise with 1 milliwatt, so the signal noise ratio is equal to the signal divided with the noise. So your signal is 10,000, your noise is 1, therefore divide it, you obtain the signal noise ratio equal to 10,000. In general, it is desired to obtain the signal noise ratio as high as possible, because by doing this, the signal quality can be improved. In the microphone, we have two stages of the amplifier. First is called the preamplifier and second is called the amplifier. The first stage preamplifier is used after the microphone and the second stage amplifier is used after the weighting network. The main function for the first stage preamplifier is to deliver the signal at a much lower output impedance that is stable for the remaining processing. The second stage of the amplifier is mainly used for the amplitude magnification as shown in this figure in order to improve the signal to noise ratio. The weighting network and the filter are located in between the preamplifier and the amplifier. Let's discuss the function of these two components. Frequency, we have learned that the human hearing is not equally sensitive to all frequencies in the audible range. For example, we know that our hearing is more sensitive around 4 kHz. However, it's less sensitive at low and the high frequency. We need the frequency weighting network, such as the A-weighted network, to modify or weight or correlate the signal in order to simulate the human hearing frequency response. Without the weighting, the microphone simply indicate the RMS value for the sound pressure and the corresponding energy content in the dB unit. Then we can convert the dB into dBA by using the A-weighting network in order to relate more closely to the average human response to noise. A-weighting is designed based on the 40-F's equal loudness control of the human hearing. The A-weighting is the most frequently used weighting because it provides the most convenient way of measuring almost all types of noise. This weighting is highest at low frequencies, where it discriminates most against the low frequency, especially the frequency below 500 Hz. The A-weighting curve versus the frequency are provided in this table, where you can see from 0 up to 500 Hz, which is recognized as low frequency. The reduction of the dB value at the low frequency is high, because our human hearing is less sensitive at this region. This weighting is lowest at around 1000 to 4000 Hz, where our hearing is more sensitive in this range. This can be observed from the data given here. Then for the higher frequency, our hearing sensitivity drops. Therefore, the reduction of the dB increase. The result after we implement the A-weighting is given in the dBA unit, and the symbol that we use to represent this sound pressure level is equal to LA. If we do not perform any weighting and use the original sound pressure level, so in this case we will obtain dB. This approach is also known as the linear weighting or the flat weighting. We can use the symbol Lin or LP to represent it. Linear or flat weighting is useful to capture the actual amount of noise. In practical, the A-weight sound pressure level will be measured much lower compared to the linear or flat weight sound pressure level. From the table, you can see the Lin, which is the linear or flat weighting. We have the zero value correction across the frequency. However, for the LA, which is the A-weight sound pressure level, the dB value, especially the low frequency region, are significantly reduced. This is because the A-weighting mimics the human hearing response to the 40-F loudness, which is less sensitive to the low frequency region. Therefore, it largely ignores the low frequency sound energy, just as our ears do. In simple, Lin represents the actual value of the sound pressure level. On the other hand, LA represents the subjective pressure level based on the sensitivity of the human ears. Let's say we perform the measurement and you obtain the Lin equal to 99 dB and the LA equal to 85 dBA. So in this case, the 85 dBA represents well to the actual human sensation to the loudness of the sound. Instead of deafening, the perception of the sound should be very loud based on the A-weighted SPL level. So bear in your mind, our human perception regarding the sound can be represented by LA instead of the Lin. So far, we have learned how to obtain the Lin or the LP by using the linear weighting or the flat weight. And also we learned how to obtain the LA by using the A-weighting. Instead of that, we can also obtain the LB, LC, LD by using the B, C, and D weighting. In simple, the A-weighting is the best scaling or the weighting to be used for many practical applications. This is because the readings on the dBA corresponding closely to the response of the ear. For medium intensity sound, loud sound, and the higher noise sound such as the jet aircraft noise measurement, we can use the BCD weighting respectively. You can read the description provided here for your extra information. Besides that, the B, C, and D weighting are provided in this table as well. The linear weighting A, B, C, and D weighting can be plotted in this graph by using the previous table data. It's less seldom for us to use the B and C weighting for the sound pressure measurement compared to the A weighting. This is because B and C weighting do not correlate well with the subjective hearing test. B and C weighting measurement are based on the equal loudness control, which is based on the experiment which use the pure tones. However, most common sound that we measure or listen to are not pure tones, but the sound is a complex signal which is made up of many different tones. This is the main reason for the lack of correlation. We have discussed about the weighting networks. Next, we will discuss about the filter. For a complex sound pressure signal as shown in this figure, this complex sound signal is actually comprised of various frequency components. Previously, we have learned that one octave band consists of 10 bands in the audible sound, which is ranged from 20 to 20 kHz. On the other hand, 1/3 octave or the 1 to 3 octave consists of 30 bands from 20 Hz to 20 kHz. Previously, we have learned that for the 1 octave band, in total it has 10 bands from 20 to 20 kHz. And the lowest frequency for the first band here is 22 Hz as shown here. And to find the upper frequency limit, you can multiply it with 2. So you obtain 44 Hz here. Also, you have learned that 1/3 octave band divide the audible sound into 30 bands as shown in this table. And the highest frequency can be obtained by multiply 1.26 to the lower frequency. To obtain the sound pressure level at each band here, from 1 up to 30 bands for an 1/3 octave, we need a bandpass filter that has the bandwidth equal to either 1 octave or 1/3 octave. Outside this bandwidth, the remaining signal will be rejected. For example, in this case, to obtain the 1 octave band spectrum here, it requires us to use the 10 bandpass filter. In general, bandpass filter is used to block out the low frequency and high frequency noise, such as this case, where only the selected region here at specific frequency is allowed to pass through. The remaining signal will be filtered out and equal to 0. Let's apply the bandpass filter, which has the center frequency at 1 kHz here. So this blue curve multiplied with the raw frequency signal, then it will only allow the signal around 1 kHz here to pass through to obtain this band, and the remaining data is equal to 0 because the frequency component here and here multiplied with the 0 of the bandpass filter give the result equal to 0. In this example, we show how to use one of the bandpass filter here in order to obtain the sound pressure level at a specific band. So if you continue the same procedure for the remaining bandpass filter, then you will obtain the corresponding band. If you apply 10 bandpass filters at 10 different center frequency, then you can obtain 10 bands as shown in this figure. This is known as the octave analysis. Next, we will discuss about the function of the RMS detector and also the time weighting or the averaging circuit. For the RMS circuit, it consists of 3 main functions. First of all, it can provide the RMS value for the signal. For a time interval T1, we can calculate and obtain the RMS1. For the next time interval T2, T3, and so on, then we can obtain the RMS2, 3, and so on. Then we can find the average of RMS by taking the total RMS from time interval 1, 2, 3, and so on, and divide with the total number of time interval. The unit of the RMS pressure is given in Pascal. We can continue to convert it into dB by using this log formula, where the P0 here refers to the reference pressure, which is the minimum pressure that can be listened by human. The RMS value for the sound pressure could fluctuate continuous from time to time. Fast mode and the slow mode are two averaging modes available on most of the sound level meters. Normally we use the fast mode for the steady noise, such as the measurement from the fan, vacuum cleaner, or the electric dill, where the RMS value is fluctuated over a range of 1 to 2 dB. In this case, the fast mode time averaging can help to even out the fluctuation. When the fluctuation of the RMS value is more than 4 dB, so in this case, fast mode is no longer suitable. We need to use the slow mode of time averaging. In simple, the slow mode selection will slow down the fluctuation, which makes it much easier to read the meter. Fast mode is normally labeled by F in the sound level meter, while the S is the label for the slow mode. Normally we will choose the fast mode, which has the time constant of 125 milliseconds, which provide a fast rating display response. However, if we use the fast mode to measure the sound level that is changing too rapidly, so in this case, it's not suitable to use the fast mode because we cannot capture the average correctly. For example, in this case, the time interval is only 125 milliseconds and you take the RMS value 1. Then you continue for the next time interval, which is RMS value 2, RMS value 3, and so on. So you can see that the fluctuation is quite large, therefore RMS 1, 2, 3 deviate a lot, and it's very difficult and impossible for us to get some meaningful reading for the average RMS. Therefore, in this case, we will increase the time constant to 1 second by choosing the slow mode. So in this case, you will have a larger time interval where the time constant is equal to 1 second. By doing that, the whole pressure changes will be captured and the average will be smoother. In this figure, it shows that if you choose the fast mode and the meter needle here fluctuated too rapidly, where the fluctuation of the value is more than 4 dB, for example from 92.3 to 97. So in this case, we cannot read the RMS value clearly. Therefore, fast mode is not suitable to read the RMS value in this case. We have to change it to the slow mode, where the fluctuation is lower and the display dB here is more stable, which is fluctuating around 1 dB here. When you are measuring the steady noise, where the fluctuation is lesser, so in this case, if you choose either fast mode with small time constant or the slow mode with large time constant, so in this case, both modes will measure the same RMS value. If you want to measure the maximum noise level produced by a car or lorry as it passes by, since the event will last for a very short time, therefore you need to use the fast mode. If you want to measure a very sharp and varying impulsive sound, we can use both modes. Nowadays, many modern sound level meters have the digital display instead of the meter display here. By indicating the maximum RMS value instead of the instantaneous RMS value, it can be used to overcome the problem of fluctuating display. So far, we know the slow mode has high damping effect, which gives a slow display movement, with the effective averaging time approximate to 1 second. Fast mode has low damping effect, which gives a more rapid display movement. The effective averaging time is approximate to 0.125 seconds. Besides these two modes, we also have I mode, which represents the impulse, and also the peak mode. These two modes are the additional time waiting, which has time constant around 35 to 50 milliseconds. We choose the impulse mode for the annoyance analysis. On the other hand, peak mode is used for the hearing damage risk assessment. This is the main difference between these two modes. In this case, we have impulse noise, where the sound pressure increases significantly and happens for a very short duration. If the duration of the impulse happens within 35 to 50 milliseconds, Then the peak will quantify the maximum SPL value here to be 127 dB. When we choose the impulse time weighting, the sound level is much lower than the peak. This is because we are computing the RMS value within this time interval, and we are taking the average for the RMS value. So if you choose the fast and the short time interval, we know that the fast mode has larger time interval compared to the short mode, which has longer time interval. Imagine the fast mode take the averaging within 0.125 seconds, while the slow mode take the time averaging within 1 second. So from here you can estimate the sound level will be reduced for the F mode and also the slower mode. Next we will discuss the function for the output, whole circuit, and also the display meter. The AC output can be connected to the analyzer or PC for subsequent analysis. Inside the PC, we can use the virtual instrument software such as the DaisyLab or the LabVIEW in order to read the sound pressure information from the sound level meter. Inside the software, we can use the oscilloscope to visually examine the sound pressure waveform. Besides that, we can also perform signal processing such as fast Fourier transform or some statistical analysis on the waveform. The hold-on circuit is used to hold or freeze the meter at its highest position. This function is useful to measure the maximum sound pressure level. The display meter shows in dB unit. The meter has been calibrated to read directly in dB relative to the reference pressure. There is limitation for the meter. No meter could indicate accurately over such a large range from 30 dB up to 120 dB and more. This limitation is known as the limited decibel range. So it is impossible to cover the entire measurement range from 30 dB to 120 dB or more. To solve this problem, we can use the range selector switch like this inside the sound level meter. By pressing the down button here, in the display meter, you see two numbers is changing, which is left number and the right number. This shows the measurement range for the dB, which means you can only measure the dB within 30 to 70. If you want to measure the sound at 80 dB, then if you press the top button here once, the number here will change to 40 to 80. And if you press once again, then it will change to 50 to 90. By doing that, now the range is suitable for the target. Previously, we need to manually control the range selector switch to adjust the measurement range. For some modern sound level meter, it even has the automatic range changing. Therefore, in this case, we don't need to manually change the level, it will do it automatically. The measurement range in this example is only 40 dB. For some good sound level meter, it can up to 50 dB of the range. These are the available buttons that you will find in the sound level meter. For a low-cost sound level meter, you have the microphone, amplifier, weighting such as A, B, C, D or linear weighting. Then you have the instantaneous RMS display or the maximum peak hold. Next you have the fast and slow mode for the time averaging. If it consists of the impulse mode, this meter can be called as the impulse sound level meter. Lastly, you have the display meter. Normally, a high-cost sound level meter consists the basic function as mentioned previously with the octave band analysis by using the 1 octave filter or the 1/3 octave filter. So far, we know that the impulse sound level meter consists of the I, or the impulse mode time averaging, which has the time constant around 35 to 50 milliseconds. This mode is useful for the sound emission, which consists of isolated impulse or contains a high portion of impact noise as shown in this figure. I mode takes the human perception of the impulsive sounds in terms of annoyance into consideration. Some standards require to use the I time constant and some use the peak. For the impulse sound level meter, you have the button here which show you the I indicate for the impulse. F is the fast button and S is the slow button. Integrating sound level meter is used to measure the equivalent continuous sound level, which is the LEQ. If you don't have the integrating meter, another alternative is by using the sound level meter using a slow response and timing the duration of the different levels. If the sound level varies randomly, this alternative can no longer be used. In this case, we need to use the integrating sound level meter. Besides that, we have dosimeter here, where it continuously calculates the maximum percentage of the noise dosage received by the worker. We can perform the LEQ measurement over any suitable time period. For example, some sound level meters consist of 60-second LEQ, which can be used for short-term LEQ sampling.